Okay, I would like to start thanking the organizers to give me the opportunity to show you what we are doing in Córdoba, in particular in Spinlock and the University of Córdoba. How is it is not working. Okay. The beginning was in the year 2003. I was a pure physicist working in the university and the National Research Council. Spinlock was born as a spin-off from the NMR group of the National University of Córdoba and the National Research Council, the CONICET. There are three principal bases. The first is, we know how to work on magnetic resonance, then we will focus in magnetic resonance. In second, this must be an innovative company, which until now it was characterized by meeting some challenge. Good?
Maybe you have to.
No, tiene que... No? Oh, no, take sorry. Okay. Then we started making researching explosive detector for airport. Sorry. We started having a partnership with other two companies. This was a project funded by the Argentine Air Force, which was succeed by the technical point of view, but not by the political point of view. Now this project is standby at least. Then we continue making some proposal to share, to fund the development of the multi-phase flow meter. I will refer especially to this point later. And this technology was finished and transferred to Kronig. Kronig is a German company producing flow meters. At the same time, Spinlock produced magnetic resonance spectrometer for multiple applications with emphasis in niche, market niche, which requires innovation. Spinlock has a large group of highly trained experts. We are 28, only 5 technicians. The other are university graduates in engineer, physics, chemistry, software management, and of all the innovative products. We pursue the quality of working life. I mean, the quality is something very, very important for us. Now the company operates worldwide in over 15 countries. First level research labs, companies have some Spinlock products in particular, mostly on food industry. In summary, we are a company fueled by the needs of the industry and contribute to the global technology and scientific process. This is what we want to do. This is the evolution. The evolution of of the Spinlock law in 12 years. I don't know, but maybe some psychologists could say what is the meaning, but I cannot say nothing about it. We want to have some always state-of-the-art proprietary technology, having patents in the US, Europe, and of course, South American countries. What we want to have is always having devices, hardware and software, tailor-made for the industry, The solution must be robust, could be desktop, transportable, and be able to be operated in the field. I will talk a little bit about, in particular, to Córdoba. Córdoba is a 1.5 million people city. In the 5 university, we have 120,000 students. It's essentially an industrial city, but due to this big quantity of students, presently Motorola, Intel, Nokia, HP, and others have been established in Córdoba, in particular for software development. There are a big potential in software development in Córdoba. Senior partners of Spinlock have more than 35 years. No, this is my age, sorry. Teaching of experience in the National University. The National University is very broad. We have practically scientists in all the science branches. And this is another thing which is very important, at least for us, is to certificate some ISO 2001 norms, but not for commercial purpose. It's just for auto-organize and have some fast and traceable outsourcing for an engineer project. This is really very hard for physicists to do this, but it's very necessary when you are going to the industry. I will point out now that our policy is essentially, we never freeze the state of the art. And this is a problem too, because it's a constant conflict between the engineers and the scientists. We think essentially in the technology, in the evolution of the technology, and the engineer want to say, but this is, it is necessary to have some intermediate point to reach something on this point. Okay. Until now, in the agriculture and food industry, we have some products. In this case, we have, this is our desktop spectrometer, and this is a 4 inches big spectrometer, which was yesterday shown by Silvio, which is located here in San Carlos, in Embrapa. Let me see. Well, we are producing some pharmaceutical controlled by NQR. Well, in the textile, this is a traditional application of an NMR, which is called spin finish. In oil and energy, we have 2 branches. One is the flow meters, and the other are the rock core analyzer. In petrochemical, we are working essentially in develop process control in biodiesel production, which is very important in Argentina right now. I will refer essentially to 2 examples of market niches needing innovation in in the core business of the food industry. For many years, NMR was used to measure oil and moisture content in oilseed, but the market needed to have some fast and non-destructible method to analyze oilseed, in particular the fatty acid profile. We innovated this, making measurements using measurement of the oleic fatty acid by TDNMR, and we developed a technique in a way that the measurement is doing with a precision of ±2%. Bruker is still working on it, and they do not reach this kind of precision until now. And also, we applied chemometry and some deep computer learning to measure protein in soya, corn, and others. The second goal was the measure of oil content and moisture in olives and pommes until some years ago. The only method available was a chemical analysis, automatic chemical analysis that consumed 12 hours to have a result. And the NMR of Bruker consumed about 8 hours because they need to dry the samples. We developed a method using signal suppression and to DILT to do this analysis in 2 minutes. This is important because the track having the olives must be checked immediately because the track cannot wait for 12 or 10 hours before have a result to pay the content, I mean the olives that they are discharging in the factory. This is our actual NMR. This is a very small NMR having a diameter of the sample of 38 millimeters in diameter, and the length of the ROI, the region of interest, is about 30 millimeters. The size are 35 times 30 times 25 centimeters. The weight is about 50 kilos. You can see here inside the device, it is really very compact. The magnet is here, and power supply, all the electronics is very, very compact in this way. And this is our inline analyzer, food analyzer, which was in a picture given by Silvio yesterday. This device have a MRI facility, and you can introduce a conveyor from this part to this, and you can measure during the motion of the sample. And the second core business actually is in the oil and gas industry. We present some rock core analyzer, which was designed essential to focalize in shale rocks. We have essentially an horizontal magnet, which could be vertical too. And also the same equipment with some modification used for the food industry can be used in this case too. We have in this case we have 2 inches of free space, and here is 1.5 inches. And this is a T1, T2 map for for, can you hear me well? Not essentially for shale rocks. 1 millisecond is about here. Sorry, but the picture is not good, but it's here, 1 millisecond. Right here? Okay. And these are some different line of multi-phase flow meter. We start with this. We made this prototype funded by ourselves. Then, in an agreement with Shell, we built this and the other. I mean, this is what at the first prototype, and this is the second one, having different technical characteristics. Well, this is a map on where Spinlock devices are located. This is a little bit old. We have more devices here in Europe and France, especially more in Spain. We sold several in the East countries. Just because of this ability to measure the fatty acid profile, because the breeders are, oilseed breeders are requiring this kind of technology, and all the big companies bought different devices from us, Syngenta and others. Well, going now to the oil and gas industry. The big challenge is like this. You have, this is a flow. This try to simulate what is the flow of a production well, having water, oil in slags, and gas. Well, this is the big challenge. The big challenge. It's not easy to reach, but we are going to try it. Generally, the liquid phases technology, painfully Coriolis, don't work well because of the gas. The robust but expensive solution is use of measurement tanks, control and measurement tanks, but this is an expensive and well, cannot be used easily even in offshore too. The more popular multi-phase flow meter use gamma ray absorption technology for the identification of fluid, but in the industry there is a strong desire to have a multi-phase flow meter without radioactive sources. The another point which is very desirable is to have a full bore design which minimize the pressure loss created by the flow meters. The other applications which are not too well fulfilled by the instrument right now are those using for the high water liquid radio, which is very important for Argentina in particular right now, and high viscosity multi-phase measuring in high viscosity oil. The principle that we propose for the NMR spectrometer we developed with Shell sorry, consists in two steps. First segment, which polarize the samples, which is called the contrast segment, and then the NMR, which measure the velocity and the water cut segment. In this first case, the liquid go from the left to the right, flow, in this part start to polarize the magnetization, but the velocity to polarize is different from the oil and water. In this case, we measuring the degree of polarization here by NMR. We can and varying the longitude of this part, we can have some equation to measure the time. Sorry? 5. Ooh, sorry. The velocity is measured by labeling the fluid, the protons here by a 90-degree pulse in a CPMG sequence, and then, well, when the fluid is flowing, the signal, the magnetization is refocalized and decays linearly. Here you can see the echo with the linear decay, and the slope of this decay is proportional to the velocity. If you extrapolate this curve to the 0 time, you will have the value of the magnetization for that velocity, and in the value of the polarization. In this prototype, this is an NMR composed by 4,200 small pieces, magnetic pieces, and have two polarization magnet in the two directions in such a way that you can measure fluid going in this direction and in the other direction too. This is possible to do bidirectional flow. This is the first prototype. Here is this prototype we built, and it is tested in Rijvaak in Holland, in the flow loop of Shell, and this is in the SWRI flow loop in San Antonio, in Texas. Well, the behavior of for a single velocity is very linear. Well, and of course we can measure all the phases in the same way. Let me go ahead. This is a comparison between what is measured for gas with what is measured by the flow loop, the SWRI, and for our flow meter, our flow regime analyzer. We have here also a picture of MRI images during the flow, where we can measure the color represent different velocities of the fluid inside the pipe. This is our last goal. We use what is called the field cycling NMR flow meter. In the flow meter I referred before, we are located in this region of the T1. I mean, we can contrast with some weight the different signals, but if we go to a low Larmor frequency, we have much better contrast between the phases. This is the main idea. I'm going in this way, from this direction with the fluid. The fluid sends a constant magnetic field, then a small magnetic field, which defines just where I'm situated here in this graphic for different contrasts, and then the magnetization for this relaxation field frequency is acquired there. Well, this is not. This is how looks the the device. Oh, what's happened now? Sorry. Oh, yeah.
Oh, it's back.
Yeah, yeah.
It's back.
It's okay. And this is the flow loop we built in Córdoba. It's a multiphasic flow loop, but no, we are not using methane by now here. And this is the flow meter. Well, I will go fastly. Well, what we have is an instantaneous response of to the change in flow velocity. We can measure accurately within 1% or even less the flow in the three phases. Generally, we test in this range of barrels by day. The cut is measured within 1 to 0.1%, depending on the value of the cut. 0.1% is when we have 50-50 and no gas. We can detect robust methane gas when the pressure is higher than 50 psi. Let me show only that, well, this is the people. Actually, we have 28 people, and always eating, And this is our new building, and thank you very much for your attention.